Turbulence is being created between the 5 galaxies of Stephan's quintet by a shockwave traveling through it at over 1,000,000 miles per hour. The intergalactic medium, the tiniest clouds of warm to hot hydrogen plasma that exist in the space between galaxies, is being driven by strange processes by shockwaves generated by a collision between the galaxies of Stephan's quintet and an intruder galaxy. Astronomers now have a clear view of the intruder galaxy NGC 7318b as it violently forces its way into this group of galaxies at a relative speed of approximately 800 km per second thanks to new observations made with the Atacama Large Millimeter / Submillimeter Array, ALMA, and the James Webb Space Telescope, JWST. That is fast enough to get from Earth to the Moon in just over 15 minutes. A recycling plant for both warm and cold molecular hydrogen gas between the 5 galaxies is being started as a result of this violent invasion of Stephan's quintet, which is causing a shockwave several times as large as the Milky Way. Additionally, astronomers discovered a massive gas cloud dissolving into a warmer gas fog that was less dense, from what could have been a collision between 2 clouds. The JWST/ALMA observations also indicate the emergence of a new galaxy and the formation of a warm gas tail. Scientists may gain a better understanding of how collisions affect the formation of stars and the evolution of galaxies as a whole and how turbulence affects the intergalactic medium if these phenomena are found. A massive shockwave is being produced as this intruder crashes into the group, colliding with an old gas streamer that was probably produced by an earlier interaction between 2 of the other galaxies. According to experts, as the shockwave passes through this clumpy streamer, it is creating a highly turbulent, or unsteady, cooling layer, and we're seeing unexpected structures and the recycling of molecular hydrogen gas in the regions affected by this violent activity. Understanding the fate of molecular hydrogen will reveal more about the evolution of Stephan's quintet and galaxies as a whole, and this is significant because molecular hydrogen is the raw material that may eventually form stars. Stephan's quintet consists of the galaxies NGC 7317, NGC 7318a, NGC 7318b, NGC 7319, and NGC 7320, which are approximately 270 million light-years away from Earth in the constellation Pegasus. Galactic interactions, including violent collisions, and the effects of these interactions on their environments can be studied best in the 5 galaxies. However, Stephan's quintet stands out from other locations where galaxies collide because these mergers typically bring bouts of intense star formation, but not in these 5 galaxies. In Stephan's quintet, on the other hand, the turbulence caused by these galactic collisions is felt in the intergalactic medium, where there is not enough raw material to cause star birth. Astronomers are able to observe NGC 7318b as it rapidly enters Stephan's quintet because star formation does not obscure collision-triggered turbulence. Using ALMA, an astronomical interferometer made up of 66 radio telescopes in the Atacama Desert in northern Chile, Appleton and the team took advantage of this opportunity to focus on 3 important regions in Stephan's quintet. The astronomers were able to create the first comprehensive picture of how hydrogen gas is constantly shaped and moved thanks to the observations. An ALMA program officer, who was quoted in the same statement, said, "The power of ALMA is obvious in these observations, providing astronomers new insights and a better understanding of these previously unknown processes." After looking into the 3 regions of turbulence, we noticed a huge cloud of cold molecules is being broken down and reshaped into a tail of warm molecular hydrogen at the center of the main shockwave, in a place called Field 6. The hydrogen is repeatedly recycled through the same temperature phases as the same processes continue. What we're seeing is the disintegration of a huge cloud of cold molecules in superhot gas. It's interesting that the gas doesn't survive the shock, instead, it just cycles through warm and cold phases, the researchers wrote. Although we do not yet have a complete comprehension of these cycles, we are aware that the gas is being recycled because the length of the tail is longer than the amount of time it takes for the clouds from which it is made to be destroyed. These shockwaves are causing more bizarre phenomena than just this hydrogen recycling plant. The team saw two cold gas clouds connected by a stream of warm molecular hydrogen gas in a place called Field 5. One of the clouds is punching through this filament in the shape of a bullet and creating a structure that looks like a ring. It's possible that a molecular cloud that cuts through intergalactic gas and wreaks havoc is rare and not fully understood. However, our data indicate that we have advanced our understanding of the shocking behavior and tumultuous life cycle of molecular gas clouds in Stephan's quintet to the next level. Field 4 appears to be the most normal and tranquil of the team's research areas, with a less turbulent environment that has seen hydrogen gas collapse, triggering the formation of a star disk there. This, according to the team, signals the beginning of the formation of a small dwarf galaxy in Field 4. It is likely that, in Field 4, large, dense gas clouds that were already there have collapsed to form new stars as we expect, the statement reads. Although Stephan's quintet's shockwave has produced as much cold molecular gas as our own Milky Way, it still forms stars at a much slower rate than anticipated. Experts believe that the theoretical models of how turbulence affects the universe will be significantly affected by these new observations. However, he added that more research will be required to comprehend the effects of high-level turbulence and the mixing of hot and cold gases. The team will need to use spectroscopic data to gain a more complete understanding of the region, even though JWST images of Stephan's quintet and ALMA observations provided a wealth of information regarding the relationship between the cold, warm molecular, and ionized hydrogen gases following the massive shockwave. These brand new observations have provided us with some responses, but ultimately demonstrated how little we do know. Future spectroscopic observations will trace the motions of the gas through the Doppler effect, reveal how quickly the warm gas is moving, enable us to measure the temperature of the warm gas, and reveal how the gas is being cooled or warmed by the shockwaves, even though we now have a better understanding of the gas structures and the role that turbulence plays in creating and maintaining them. In essence, we only know one side of the story. It is now time to acquire the second. Well, that's it for today. If you enjoyed the video, please hit the like button. If you have any suggestions, leave them in the comments section. And if you enjoy our content, and never want to miss a video, hit the subscribe button. Thank you for watching.